and the current and the voltage sensing also play an important role to maximize system performance, grid stability, and resiliency. Technology TI offers include precise current and voltage sensing. They also have the edge processing and communications, and that connect the grid and the cloud while enabling compliance with standards such as Open Charge Point Protocol and the V2G standard. They have a wide range of connectivity products supporting Wi-Fi, Bluetooth, Wi-SUN, sub-1G protocols, as well as Ethernet, EtherCAT, different communication methods to better processing data at the edge and also communicate that data. Meanwhile, TI has the Edge AI solution for real-time fault detection and monitoring. So last but not the least is the battery management. TI keep working on this part is to deliver the best-in-class battery monitoring and the energy storage capability. So in today's session, I'm going to kind of more focused in the high voltage power conversion by giving you two specific examples how we do things in the solar energy space, and to show you how TI can work towards a smart and flexible and efficient energy infrastructure used in the microgrid systems. So first of all, let me show you a picture. This is one representation of a smart grid ecosystem. And in the past, if you talk with me, show me this picture a couple of years ago, I would think this probably would be a little bit futuristic, but now it's the reality. So this shows a typical household that can be everywhere. So in this place, you could have the solar energy system that generate the light, the energies through the sunlight. And also you have the energy storage system that can locally store the energy. And then instead of just kind of getting all the energy from solar or the grid. And in addition, you have the EV charging, not only charging your electric vehicle, but moving forward, you have a chance to leverage the battery in the car and backfill the power the house. So, and this is a very, in my opinion, is a typical microgrid system, and that can be self-sustainable. And today, in this use case, I want to kind of drive into give you some example of how TI gets better solar energy system and the energy storage system in the next couple of slides. So, and before I get there, I want to talk about the challenge, overall challenge we're seeing in the market. And speaking of the challenge in the solar system, right, it's about the capture and convert the solar energy more safely and efficiently. That is kind of a overall challenge statement. And the other challenge we see in the battery management system is how to optimize energy storage to access energy when and where needed. So here in the next slide, I'm going to talk about two TI reference design showcasing some unique innovation TI did in terms of the microinverter and also hybrid string inverters. So let me start with having a look into how solar microinverters have been done traditionally. The microinverters has been used on the rooftop or balconies, especially in Europe, that had been all unidirectional. Electrical power generated by solar panel, when exposed to light, was converted into a first stage from typical power panel voltage in the range of 20 volt to 50 volt, then into a DC bus voltage, typically 400 volt. There are different configurations for the microinverters. Then you will see one microinverter supporting one PV panel, 2, 4, or even more. Those PV panels are connected to an individual DC boost stage. The power level ranges from 400 watt for a single panel to 1.6 kilowatt and even more for a quad channel configuration. Then the power aggregated at the DC bus is summing up and is converted into an AC power that can feed into a single phase grid with 110 volt or 230 volt system, depending on which region in the world you operate the microinverter. So far, all this is unidirectional from PV panel side to the AC grid. The topologies that have been used on this are very often current source inverters in flyback or push-pull configuration. Those are really low cost. However, have the disadvantage that magnetics and the electrical cap components are big, which drives power density low, and overall, these converters have a low efficiency in the lower 90% range. With the trend in the market, we have observed that to combine the solar energy generation with battery energy storage system, which leads to the concept of a kind of hybrid microinverter. Think about during nighttime or when sunlight change significantly, it would be nice to have an energy storage system that can provide energy into a household where extra energy is needed. Since the voltage and the power levels at each input are pretty similar for PV panels and a 48-volt battery storage system, a bidirectional DC-DC stage would allow to mix and match battery and the PV panels. Key difference here to the traditional configuration is that you need each DC-DC to operate bidirectionally, so to allow energy storage from panel to battery. Also, to allow the energy from AC grid can be used to charge a battery, the AC-DC also need to be realized bidirectionally. Sorry about that. So that means the topology needs to change from the current controlled converter to voltage controlled converter, also called as a VCS. TI recently released a new microinverter reference design called the TIDA 010933. It was to build a highly efficient bidirectional hybrid microinverter at a very high power density with low cost in mind. So let me dive into the details. First, by showing you, take a look at the block diagram for this reference design. So I would like to explain the operating principle of this first. As mentioned before, we have configurable inputs and outputs. So we have up to 4 PV panel inputs that can operate with 400 watt panels with a maximum current of 14 amps. This is typical value for PV panels, and over 95% of panels available in the market today would meet this requirement. Each of the ports can be configured to operate with 48-volt battery packs with charge and discharge capability of 400 watt. Then on the right side, now you will see each of the ports can be configured to operate with 48 battery packs. That's charge with charge and discharge capability of 400 watt. Yeah. Then on the right side, on the left side, you'll see the connection to grid with the plug outlet. The maximum power this converter can sink and source into and from the grid is 1.6 kilowatt. The design is done in 3 stages. On the right, you'll see the full bidirectional DC-DC buck boost stage that takes the voltage in the range from 30 to 60 volt DC and convert this to an internal first bus voltage set to 75 volt. The second stage is the bidirectional CLLC stage that converts from 75 volt to the secondary DC bus voltage of 400 volt. This stage is the resonant converter with a transformer in the middle, and it has a full bridge on the 75 volt side and a half bridge on the 400 volt side. On the 75 volt side, we are using 2 LMG 2100, a fully integrated GaN half bridge device with only 4.4 milliwatt on resistance. On the 400 volt side, we are using 2 LMG 3522, 650 volt rated GaN FET also with integrated driver, and on resistance of 50 milliwatt. When operating from 75 to 400 volt, the LMG 2100 full bridge operates as a driver for the resonant transformer, and the 2 LMG 3522 are operating as active synchronized rectifier. When operating from 400 volt down to the 75 volt, 2 LMG 3522 operates as driver for the resonant transformer, and the LMG 2100 full bridge operates as a synchronous rectifier. The third stage is a totem pole AC/DC realized with 2 LMG 3522 GaN FET and the 2 slow speed MOSFET. The GaN FET switch as click the wrong button. So the GaN FET switch at a high frequency of 125 kHz, whereas the MOSFET switch as the line frequency. So the design challenge are making each stage operate at high efficiency, bidirectional, and still achieve a high power density. Operating each stage at fairly high switching frequency, which is possible done by using GaN FET, allows a reduction of size for magnetic components. So then let me show you a couple of efficiency measurements of this design. So on the screen, you'll see the block diagram, just showing the complete inverter design again. When we look at the first stage, we can see following efficiency versus input power applied from the panel. The 3 different graphs represent different input voltage to the DC-DC boost stage. Over a very wide range, the efficiency is way above 98.5%, even for low input voltages of only 30 volt. It has to be kept in mind that a 400 watt panel have fairly constant output voltage in the range of 33 volt. Since the PV panel is a current source for which the current changes mainly with light exposure, the assumption to operate between 30 to 40 volt is quite accurate. This stage has a very flat behavior over output power, which is very good. With the definition for weighted CEC efficiency, which takes certain coefficients at certain percentage of power levels and sum this up. The calculated weighted CEC efficiency for this stage is about 98.6%. Then, when looking at the complete quad boost stage, we see the efficiency of the DC-DC boost plus the CLLC stage combined. As can be seen in the chart, the curve is well above 96% over a very wide range, and the calculated weighted CEC efficiency for this stage is around 96.5%. Then let's look at the totem pole AC-DC stage. Here you'll see the efficiency graph in the top right corner. The efficiency of this stage alone is close to 99%. The calculated weighted efficiency is around 98.7%. If we combine all together, the complete converter shows from DC input all the way to AC output a weighted efficiency with over 95%, which is remarkable for a fully bidirectional converter compared to the low-cost unidirectional current source inverters that achieve often only in lower 90% range. Okay. So let's get to another solar-related reference design. What's shown on the screen is the other solar design that is, instead of it microinverter here, we are showing a hybrid single-phase string inverter with battery energy storage systems. So you'll see on the right bottom, 2 PV string inputs capable to operate each PV string's input with current up to 14 amps. The maximum open current voltage at each string input could be as high as 500 volts. This voltage is only visible when the strings are not loaded. In residential use, very often 400-watt PV panels are used. The typical maximum power point voltage of nodes is in the range of 33 volts, meaning if 10 PV panels are connected, the voltage present on a string input would be around 330 volts. 10 panels would also mean the power available at each input can be as high as 4 kilowatts. For 2 strings inputs, we are at 8 kilowatts. We rated this design when we started for 7.2 kilowatt, and actually later on, we realized actually 8 kilowatt on the PV string input side can also be achieved with margin. For output of the string DC-DC boost stage are connected to the common DC bus that is rated to work at 400 volt normally. The second building block we have in this design is the bidirectional DC-DC that is connected to a battery pack that can range from 80 volt up to 320 volt. But also 400 volt can be possible since DC bus voltage is nominally 400 volt, but it can be higher. The current to charge and discharge the battery pack is rated for 330 amps. For a 240 volt battery pack, this would translate into a maximum charge and discharge power of 7.2 kW. The third building block is the bidirectional AC-DC, which is rated for single phase up to 3.6 kW only. The reason was that we limit the output current in this single phase application to 16 amp RMS. At 230 volt, this translates into 3.6 kilowatt. Okay, sorry. All right, then let me dive one level deeper into how we partitioned this reference design and how we implemented the different stages. On the left, you will see the string DC-DC boost stage. They are realized with the LMG3522 30 milliamp ohm GaN FET with integrated driver. The diode is a silicon carbide Schottky diode. Since the control MCU is referenced to the negative bus voltage, the string current can be measured with an INA 181 across a shunt resistor in the negative rail in a non-isolated fashion. The voltage measurements on PV strings for feedback are also non-isolated. The booster stage are operated at 120 kHz. Important to notice that the inputs of the GaN modules with the integrated driver are non-isolated and are driven by logic buffers only. I want to highlight that in general, the complete design has been trimmed for low cost, system costs, and avoid isolation whenever possible. In the middle, we can see the bidirectional DC-DC for the battery port. It has been implemented as an interleaved stage, meaning two converters realized each again by two LMG3522 GaN devices are operating in a 180-degree phase shift to each other. Each one operates at 60 kilohertz, which results in a 120 kilohertz operation for the two interleaved legs. Here, we had been using the isolated amplifier AMC 1302, which can be easily supplied from the GaN device on the top of each leg. No additional isolated supply needed for the AMCs. On the right, you'll see the AC-DC stage. Here, we decided to build a configurable AC-DC. There are three possible modes of operation. First one can be full bridge in unipolar PWM modulation, or it can be full bridge in bipolar PWM modulation. And lastly, it can be configured as a Herrick topology. All have pros and cons, and we wanted to give in this design the flexibility to have one AC-DC stage that can be operated in three modes, so we can compare the results. It can be said that the Herrick operation provides the highest isolation or common mode rejection to the PV panel side. This is important because any peak voltage built up at the panel side can cause a ground fault DC currents on the AC side, which would trip the converter. That's why good common mode rejection in the AC-DC stage is beneficial. The full bridge operation with bipolar modulation offers second best common mode rejection and is also a good choice. All right, let's have a look at how the efficiency look like on the different stage of this design. We start with the DC-DC boost used on the PV strings. The schematics in the middle illustrate which block we are looking at. In all, show measurements, the DC bus voltage was set at 400 volts. The switching frequency of the up converter has been set to 120 kHz. On the top left, you'll see the efficiency versus output power into the DC bus. It can be seen that the converter operates well with as low as 50 volt input voltages. With the limitation, that the input current was limited to 14 amp. We see the output power is of course only 700 watts. It can be seen that the efficiency is already in the range of 96%. With increased input voltage from 150 volt up to 350 volt, the achieved output power increases gradually to 4.9 kW for 1 PV input. The efficiency is at really remarkable 99%, clearly showing the benefits of GaN. On the top right, same efficiency plots are shown, but versus the input current to see that efficiency is very constant over a wide input current range and matches the current source behavior of a PV panel very well. On the bottom left and the right, you'll see the temperature profiles we derived during the efficiency measurement. The LMG3522 has an integrated temperature sensor which allows to report out the actual temperature measured at the junction of the GaN device, output to an MCU for monitoring purpose. It can be seen that the temperature inside of the GaN device is not exceeding 70 degrees C, which gives a lot of thermal margin to the design. To get information about the thermal behavior of the cooling system, we measure the heat sink temperature at the indicated location with temperature sensor ICs. The heat sink temperature is not exceeding 40 degrees C, even at the full load, which demonstrates the robust cooling concept of the design. Same temperature measurements has been done on the Schottky. So the same temperature measurement has been done on the Schottky diode to see if a critical condition is happening. Okay, now probably let's look very quickly to the bidirectional DC-DC for the battery ports. The schematic in the middle illustrates again which block we're looking at. In all show measurements, the DC bus voltage was set to 400 volt DC again. The switch frequency of the converter has been set to 60 kHz for each interleaved leg, resulting in an effective converter frequency of 120 kHz. In the top graph left, we see again efficiency versus output power into the battery for the buck mode, meaning we mimic the charging of the battery system. On the top right side, we have the efficiency versus charging current, which ranges up to 29. On the bottom, the reverse operation means boost mode, or in other words, discharging of a battery is given. On the right, efficiency versus discharging power. On the left, you will see the efficiency versus discharging current. It can be seen that the efficiency are very constant and above 98% over a very wide current range and even at the low battery voltage of only 80 volts. The converter shows around 97% efficiency for charging and discharging, a very impressive behavior which goes back to the low conduction and switch losses of GaN when running at fairly high operation frequency. I also want to mention that the measurement on the maximum output power had been limited to the measured equipment we used. Given the graphs and the temperature we have seen during the measurement, we feel very confident that this converter can achieve 9 kilowatt charge and discharge power at a battery voltage of 320 volts. So lastly, after a lot of performance measurements, I want to get to some design highlights for this reference design. The complete design is shown on the picture on the right, which is a real EVM system. So the design is partitioned into an AC-DC and the DC-DC portion. The total solution is size of 29 centimeter by 28 centimeter. All control algorithm for DC-DC boost, bidirectional DC-DC, and a configurable AC-DC are run on one single TMS 320 F28039C, a real-time microcontroller. We had been using a control card that plugs into the main board, and the MCU is the reference to the negative supply of the DC bus. Because of the architecture used and the switching frequency fairly high, which is possible with GaN, the need for huge electrical blocking capacitor is not that much. Running GaN power devices at high switching frequency allow to use small-sized magnetic components, which in turn drives the solution size down and allows for high power density. And in the table, you can see all specifications for the string inverter for all subsystems. If you compare this to the existing design with traditional implementation with silicon FETs, the design has unprecedented efficiency at this power density at the power level defined for the design. Okay, so with all that, let me kind of take a break and give you a quick summary talking about this microgrid and the power topology. So first of all, bidirectional power conversion is important consideration for safe and efficient power transfer in solar power grid with energy storage. There are unique advantages of bidirectional power topology that can enable safe, efficient transfer of power between the grid, PV array, and battery management systems. So a microcontroller such as the C2000 devices are popular for such power topology. Then on the power electronics, silicon carbide or GaN-based devices can help ensure the adaptation of a bidirectional converter. In a storage integrated microgrid system, a battery's primary function is to store PV panel and return power to the grid when prompted. And a hybrid inverter would help achieve great efficiency. More important with microgrid since multiple power conversion occurs. So as you can see in the previous designs, both designs are leveraging TI GaN devices. So here we put together one-page summary talking about the benefits of TI GaN over the silicon. So first of all, the GaN offer higher efficiency. The overall efficiency used in the reference design exceeds 98%. And because of a higher switching frequency, that allows for smaller magnetics and allowing for 40% size reduction. And over 2x the power density of equivalent silicon-based designs. So by leveraging TI GaN device, there are we have a number of reference design our customers can get started with. So earlier, the mentioned bidirectional microinverter can be found on the left. And we also talked quickly about the single phase string inverter in the middle. And also we have the MPPT charger controller design on the right, which was not mentioned in this session. Okay, then we got a little bit more time. Let me talk very quickly about some new, very exciting GaN devices TI just released. So here on the screen, you'll find the two devices TI released supporting up to 100 volts. And on the left side, it's the GaN half bridge with gate driver integrated, which is the LMG 2100. On the right hand is the single GaN FET with gate driver, and that is the LMG 3100. Both are in the package QFN supporting up to 100 volt. And it also have the protection feature UVLO. And a very unique feature for this, for TI GaN devices with integrated gate driver and also have the integrated bootstrap. So for the half bridge, the on resistance is limited to 4.4 milliohms. And for the single GaN FET with gate driver, needs 1.7 milliohm on resistance. So, okay, here we have a little bit more detail talking about the product overview. So I probably just kind of highlight a couple of things here. And as you can see on the right hand, this new TI GaN device are with exposed GaN dies for heatsink on top. And then at the bottom, you have a large cooling heat sink area for heat dissipation. And similarly, this is the one-page diagram for the LMG 3100, and different from the previous one, which is the half bridge, and this is a single chip GaN power state GaN FET with integrated driver. And speaking of integrated gate driver, what's the key benefit? So having an integrated gate driver can reduce overall inductance by physically having the driver and the FET close together. This would allow for faster turn on and turn off, meanwhile lower the dead time losses, so to improve the overall efficiency and the power dissipation. So to the end, please let me kind of use this slide to make a quick conclusion. Microinverter and string inverters are trending to bidirectional for battery energy storage system and high voltage density, high power density, and smaller, lower cost passive components. GaN can enable bidirectional topology and increase power density and efficiency at equivalent cost to silicon MOSFET solutions. TI GaN's integrated gate driver, over temperature and short circuit protection allows simple system integration. GaN's ability to allow faster switching and higher power density address power conversion systems that can enable smart, flexible, and efficient energy infrastructure. So if you're looking forward, we look forward with all the technology TI provides, we can enable the energy transition. So we expect to see more to come in the solar space, energy storage system space, metering and management, and also the EV charging. So we're very excited about the transformation of the energy evolution, and look forward to work with all of you and to build a bright future. Thank you very much.
Well, thank you, Michael. That was a great, really in-depth presentation, and I think it'll be a real benefit to the design engineers in the audience. So are you ready to answer some questions?
Thank you, Dale.
Yeah. So are you ready to answer a few questions?
Yes, absolutely.
All right. So first one I have here, this came in kind of late, so I know you covered a few different topologies, so maybe you can tell which one it was. Is the DC-DC converter a buck or boost or buck boost? Okay. And then they also asked, what topology did you go for in this design, and how did you decide on that topology?
Okay. Yeah, that's a great question. I assume this probably related to the microinverter reference design we talked as the first example. Mm-hmm. In that design, the DC is really depending on which direction we go. When it's configured as a microinverter, the energy comes from the solar panel to the grid. In that scenario, the DC-DC is configured as a boost stage. So that is a boost converter. But when that reference design is used as kind of an energy storage system, the energy flow from the AC grid to the 48-volt battery system, then that's DC-DC stage would act as a buck converter. And speaking of the choice of topology, actually, I'm not the one who worked on the design myself, but our design team, system design team, actually did a very detailed analysis comparing the pros and cons of different topology in terms of performance, cost, and we came up with this final approach. And TI did publish a couple of good application notes comparing the benefit, the advantage, disadvantage of each power topology used in the solar system, energy systems. So maybe as a follow-up, I could share the link to that application note where we talk more about, the decision-making process, and hopefully that can be useful.
Okay, yeah, so great question and answer, thanks. Next question is, can these be used to power a device directly with controls to turn them off? For example, if the voltage falls below what you're expecting, or are they really meant to always be used in type of a grid application of some form?
Okay. Sorry, could you repeat that question? I'm not sure if I fully captured it.
Yeah, so they were asking, I mean, your examples here are about using these power devices in a grid